Welcome to lecture 7.8, the two-dimensional wave equation. Okay, so let's start out with an overview as to what the wave equation models. So suppose we have a vibrating square membrane of length L. Now it doesn't have to be square, it could be rectangular of length L1 and L2, but let's just say it's square to make things easier. So think of this as like a trampoline. So we have a trampoline down here, and say x goes in this direction, y goes in that direction. So this is the point 0, 0, and up here this is the point L, L. Okay, and then U is a displacement, the vertical displacement at some position x, y, and time t. So this little point of the trampoline, if people are jumping on top of it, it might be going up and down like this, and that's going to be measured by this function here. So then U satisfies the following initial and boundary value problem for the wave equation. This is the wave equation at left. This is just physics, the fact that U will satisfy this. These are boundary conditions. You've seen this before. This first one says that the displacement at y equals 0 is 0. That's this front edge for all time t. And this boundary condition, this equals 0, says that the displacement at the left edge along here is equal to 0. And now we have initial displacement and initial velocity. So a general rule of thumb is that for every derivative we need an initial or boundary condition. So we have 4 spatial derivatives and we need 4 boundary conditions. For the heat equation we only had 1 time derivative, so we needed 1 initial condition. Now we have 2 time derivatives, so we need 2 initial conditions, initial displacement and initial velocity. And it makes sense that if you want to completely determine the waves here, it depends on not only the initial displacement, for example, this thing could be sitting here at rest, but also whether or not people are initial velocity, or people jumping on it at rest, or people just letting it sit. Okay, so let's do an example. Let's solve the following initial and boundary value problem for the wave equation. So here's the wave equation. 4 boundary conditions are 0. And then this is an initial condition, and the initial displacement is given by this, and the initial velocity is given by 0. Okay, so let's actually sketch what this looks like. So, so we have a trampoline, which is square, and of side length pi. That just makes the math easier. So x is in this direction, y is in this direction. This is the point 0, 0. And then this thing here says the initial displacement is given by, this is a parabola in both directions. So it's going to look something, so you can think of it as, so it's, I don't know how accurate, I don't know how good I am at drawing this, but it should be something like this. It's like a bubble. So we take this square membrane, we lift it up like this initially, and then initial velocity is 0 means we let it go. So we pull this thing up in this dome shaped, and we let go, and this thing's going to bounce back and forth like that. Okay, and this is the PDE that it solves. The boundary conditions saying that these are fixed at 0, initial displacement, and initial velocity. Okay, so we'll solve this like we always solve these, and actually most of the math we've already done, especially in the 2D heat equation. So this will actually be pretty short. So let's assume that let's assume that we have a solution which is a function of position times a function of time. Okay? And now we're going to plug this thing back in. Let's see what I want to do. So I'm going to write through this quickly. So UTT equals F times G double prime UXX. Actually, how about just UXX plus UYY? I'm going to write that as, so this is the Laplacian of U, which is the Laplacian, I should put a square there, Laplacian of U, which is Laplacian of F times G. Okay? And now we have these 4 boundary conditions. I think what I'm going to do now is I'm going to write my 0 boundary conditions. I'm just going to write them down without actually deriving them because we've seen them before. F of x0 equals 0. F of 0y equals 0. F of f of x pi equals 0, and f of pi y equals 0. We actually have something else now. We don't have to use this at this point, but we have a 0 initial condition. So let's use this too. So why the heck not? So 0 initial condition, again, my own term. So ut of x, y, 0, this is f of x, y times g prime of 0 equals 0. And that tells us right away that g prime of 0 equals 0. So we have these boundary conditions, but we also know this. And again, we don't have to use this till the very end. It just makes things easier to do it earlier rather than later. Okay, now let's plug this thing back into our PDE. Okay, so UTT is FG. I'm going to actually move myself up so I have a little more room. So we're going to plug into PDE. So UTT is FG double prime equals C squared times, let's just write the C squared times the Laplacian of U. So that's C squared times Laplacian of F times G. So let's divide through by C squared FG. C squared, this is the same thing, exactly the same thing as what we did for the heat equation in 2D. It's just instead of, the only difference, literally, is instead of G prime, we have G double prime right here. So when we do this, we get, on the left-hand side, we get G double prime over C squared G. And on the right-hand side, we get Laplacian of F over F. So, as before, this is a function of time, and this is a function of space, position. So this thing does not depend on position, and it's equal to this thing that does not depend on time. So it better be constant. So this is our eigenvalue equation. Same as before, just we have one extra time derivative here. So we get two ODEs as before. So first we get an ODE, or I guess a PDE in F. So we have Laplacian of F equals lambda F, and then our four boundary conditions are F of x0 equals F of 0y equals F of x pi equals F of pi y equals 0. So that is the Helmholtz equation, and remember we solved that in the last lecture. We took a 12-minute detour or so, and then we solved this. So we know the solution. So we don't have to do it again. So the next one is an ODE in G. So we have this thing here. So this tells us that. So this is G double prime equals C squared lambda G. And I'm going to put, and we have a boundary initial condition, this thing over here. I'm going to put this over here. So this is, this is G prime of 0 equals 0. Okay, so this is something that we know how to solve. So recall that the solution to the first one was that lambda equals negative m squared plus n squared. And f was, let's try that again. F of x, y was, what was it? Sine of mx times sine of ny. So we can actually say even more about this. We can say this is equal to negative c squared n squared plus m. Oh, let's be consistent. Oh, that's fine. N squared plus n squared times g. Doesn't matter what order you're at, n and m, right? So now we can solve this. Let's solve. Let's solve g double prime equals this whole thing times g. And this, it looks messy, but it's very simple actually. This is just a negative number out in front. This is sines and cosines. So, this is simple harmonic motion. Think of this thing as my omega squared. So now we know what g is. So g of t is, actually, let me actually do that out to the left a little bit. So g of t equals, I should probably say a times cosine of omega t. So that's what's the square root of this? That's c times root m squared plus n squared. So cosine of c times the root m squared plus n squared times t plus b times sine of that same thing, c times m squared plus n squared times t. Okay, so this is what g is, but we also have this initial condition right here. Okay, so what does this tell us? So notice if this condition were g of 0 equals 0, then we would plug in 0, and this would become 0, and we would get g of 0 equals a equals 0. G of 0 being 0 would kill off the cosine term, okay? However, g prime of 0 does the opposite. G prime of 0 kills off the sine term. And I'm not going to do this. If you want to check on your own, you're encouraged to. But let's try to do it in our head. G prime of 0, take a derivative and plug in 0. What happens? So you take a derivative and you get g prime is a times this constant times sine of this. You plug in 0, that goes away. Plus b times some constant. Actually, let's do that. Let's do an intermediate step. So g prime of 0 is going to be, I claim that's going to be 0 plus b times, so this is going to come out, b times c times m squared plus n squared times cosine of 0 equals 0. So g prime of 0 equals 0 plus b times some non-zero constant times 1 equals 0. B must be equal to 0. So that tells us that we know what g is. G of t is this thing, except the sine term is equal to 0. So g of t is cosine of c times n squared plus, actually let's do my m squared first. I'm using the wrong color. M squared plus n squared times t. Okay, so now what we have is we have a solution of this form. We know that for every lambda of the form negative m squared plus n squared, we have a solution. So we have u mn of x, y, t equals f m n of x y times g m n of t, which is, let's write this out, so this is sine of mx times sine of ny times cosine of c m squared plus n squared times t. So that is a fundamental solution. Think of this as, so we have this is, remember how for the heat equation, how we had, sorry, for the 1D wave equation, we had a fundamental frequency, a solution for each sine of nx. Well, we have the same thing, just we have a fundamental frequency in the x direction and in the y direction. Okay, so now we know enough to say what the general solution to this PDE is. So recall that for every m and n pair, we got a solution that looked like this. I called this umn of x, y, z, not z, that was just a habit, x, y, t, sorry about that. So this is like our fundamental solution for m and n. So in the one-dimensional case, we just had this for only the x direction, but now we have the x direction and the y direction. So by superposition, we can take arbitrary linear combinations of this and get a solution like this, assuming that this actually converges to a function. So this double sum just means that we're summing over all m and all n. It doesn't matter if we write it like this or if we could write it as a single sum. Remember what we did before, we wrote it as a single sum. It just said m and n are greater than or equal to 1. So it's the same thing, it's just a notational difference. So this general solution represents these 4 boundary conditions and this initial condition. Remember, we used this early because I recommended it. You didn't have to. If you had instead saved this till later, if you had not used this early, instead of getting a cosine term here, you would have a cosine and a sine term of t, and that would mean instead of having one coefficient bmn, we would need a bmn and an amn or cmn, whatever you want to call the second term. So it's much easier to just leave it like this. So now we will actually use this last condition right here. So this is the final initial condition. So u of x, y, 0. So let's plug this in. So when we do this, we have, how do I want to write this? Sure. So we have this double sum, m equals 1 to infinity of n equals 1 to infinity. That should be it. Oops. Yeah, n equals 1 to infinity. So when we plug in 0, the cosine term goes away, and so we have bmn times sine of mx times sine of nx, and okay, so what is this? This is a double sum, so we're summing over every possible pair sine m times sine n, or sine mx times sine, oh, I forgot that this should be a y, not an x, sorry about that. Okay, so this thing, convince yourself that this is simply, can be written as a product of let me call this beta, or bn sine of nx times n equals 1 to infinity. I need something else. How about a beta, I keep forgetting, sorry, the sine of m, bm, beta n times sine of ny. So convince yourself, you may say, how the heck did I factor this as that? Convince yourself that these things are the same thing. That if bn or bmn is bm times beta n, so in other words, if this constant is this constant times this constant, then both of these things are the same thing. This is a sum of every single sine mx and sine ny, and the thing on the right is also a sum of every, when you multiply, FOIL this out, add forever, you still get the same thing on the left-hand side, an infinite sum of sine mx times sine ny. Okay, so why do we do this? We do this because this thing is equal to x pi minus x times y pi minus y. And we know how to write this thing as a Fourier cosine series, or we know how to write these things as Fourier sine series. Okay, so this is just, let's write it here. So this first one is that n equals 1 to infinity of 4 times 1 minus negative 1 to the n. I left myself enough room here. Pi n cubed sine of, I should say sine of mx. I've been just a habit calling these n. This is m. And then the next one is going to be, this should be an m. It really doesn't matter actually at all. I mean, whatever index I call it. N equals 1 to infinity of 4 times 1 minus negative 1 to the n over pi n cubed times sine of ny. So we have started with this. We started by plugging in 0 into here. We get this doubly infinite sum of sine of mx times sine of ny, which we can factor as a product of sine of a sine series in x and a sine series in y, which is this times these parabola in x and this parabola in y, which we can write this as a sine series in x and a sine series in y. And now, because this coefficient is just the product of these two things, bmn is that creature times that creature. So bmn is big B m times beta n, which is, so let's multiply these things together, or multiply this times this. We get 16 on top, right? So this is 16 times 1 minus negative 1 to the m, 1 minus negative 1 to the n. And on the bottom, what do we have? We have a pi squared, we have m cubed and n cubed. So we have pi squared times n cubed, or m cubed times n cubed. And this thing, so what is this thing? We can actually reduce this. This thing on top, if m is even, this is 0. And if n is even, this is 0. Otherwise, this is 2 and that is 2. So the whole top is 64. So this is 16 times something that's either 0 or 2 times something that's 0 or 2. So this really is just 64 over pi squared m cubed n cubed. And I could probably extend that, assuming that n and m are even. They're both even. Otherwise, it's 0. So else. So really, what this is so this coefficient is only going to be non-zero when m and n are even. Okay, so now we can write, let's plug this thing back into here. So the general solution is, or I should say the particular solution is u of x, y, t is this double sum. Let's actually write it, how about we write it like this? Over all n and m are even, so it's a sum over all even m and n, and now we can write this as 64 over pi squared m cubed n cubed times sine of mx sine of ny times cosine of c. I hope I run out of, or have enough room here. C times root m squared plus n squared times t. And that, this thing right here, is the particular solution to this initial and boundary value problem for the wave equation. And notice, as time goes on to infinity, this thing is not going to approach a steady state solution because this cosine is going to oscillate. Notice that the frequency of the cosine waves is going to be different than the frequency of the sine of mx and sine of nx. So again, a little picture as to what we have is we have this trampoline that's in this sort of balloon initial shape, something like this, and we've stretched it out like this, and we've let it go, and so this thing here is the frequency in the time. So this represents the frequency in the time direction, and this represents the frequency in the x direction and in the y direction.